Being so kind to invite me here to talk today. I'm very happy to be here. So I'll talk about this high throughput screening of 2D topological insulators and ferromagnets. The screening study is mostly based on this computational 2D materials database, which we have set up at DTU. So I'll talk a little bit about that to begin with, what it is. And then I'll talk about how we use this, how we can do an automated search for topological insulators based on this. I mean, it's known how to do this for a particular material, but it can be a little bit tricky when we want to automate such a search. Then I'll move on to something a little bit different, namely the subject of magnetism in 2D. It turns out that it's a little bit more tricky than in three-dimensional materials, because we're used to, in 3D, if we do a DIPC calculation and the ground state is magnetic, then we expect that there will be a spontaneous symmetry breaking and the material will be magnetic at some finite temperature. But in 2D, it's very different due to the Ferromagnetic theorem, which tells us that we cannot have spontaneous symmetry breaking in 2D. So we need to have an explicitly broken symmetry, and then makes it a little bit more tricky to calculate critical temperatures for magnetic order in 2D. And then I'll use this to predict some new two-dimensional ferromagnets, also based on this database, but also show a little bit preliminary results based on the ICSD. Okay, so the computational 2D materials database, it's purely computations. And the idea is very simple, maybe even a bit naive. We just take a lot of known 2D materials, and we characterize them by a particular prototype, with graphene, MOS2, and so on. There's a lot of different of these. And then we do a combinatorial lattice decoration. For example, if you take MOS2, we can replace molybdenum by other transition metal atoms, or we can take sulfur and replace it by other chalcogen or halogen atoms. And then we run everything through a workflow, and if it looks reasonable, we put it into the database, and then we calculate various properties. And currently we have 3,700 materials, but it's still growing. Just a little bit on the workflow. Once we've set up a material by this combinatorial lattice decoration, we of course relax the cell and all the atoms. Sometimes it just disintegrates and we discard it. Sometimes we figure out, okay, it's already in there. We may start from a starting point that we didn't know would go to some other structure. Then we classify it by the symmetry and the prototype, and then we calculate the thermodynamic stability. Particularly, we calculate the heat of formation with respect to some standard references, and then the energy above the convex hull. And we characterize materials as being thermodynamically stable if they have a heat of formation which is less than 0.2 eV. It means that they're not completely stable, but they can still be interesting even if the heat of formation is positive. For example, silicene has a heat of formation which is half an eV per atom. So it's really unstable, but still people have managed to stabilize it on a silver surface. And this has spurred a lot of interest in this material. So materials can be interesting even though this such a study here doesn't predict stability. Then we also calculate dynamic stability, simply calculating the phonons at the Brewing zone corners. And if some of these are imaginary, we know that it will distort to some other structure, and we discard it. So once we have a material which is that we regard as stable, we calculate various properties like anisotropy, predicted density of states, and band structures. Then we do slightly different things depending on whether it's insulating or metallic. For example, if it's insulating, we would calculate the DW band structure also and the optical absorption spectrum based on the Biedesel-Pita equation. So we have some 200 Biedesel-Pita equation calculations in here, but we only do this if the unit cell does not contain too many atoms. Otherwise, it's just too hard. So of course, I mean, this will result in a lot of different materials, which are somewhat ridiculous because they will only exist in a computer. There will never be no one will ever be able to synthesize them. But it still comprises a nice playground to look at different properties of 2D materials. And of course, we get all the known 2D materials already in there, and then we also have a set of new materials which we predict to be very stable, but which have not been synthesized yet. And here's just a few examples of properties. Band structure of MOS2, optical absorption spectrum. You see these famous A and B excitons lying down here below the band gap, and we have structures like this for many of the materials. And everything is, of course, open and can be browsed online at the web address I showed you here. So comparing to other databases, we don't have a lot of materials. There's just a few of the known materials databases. These contain a lot of materials. So 4,000 materials is really nothing compared to the number of materials in these databases. The scale probably should be logarithmic here. But then, on the other hand, we have a lot of properties for each of the materials in the database we calculate. For example, piezoelectric tensors and Born-effective charges and so on. Here's just an example of what you can use it for, even though that some of the materials are not stable and probably never will be synthesized. Then we can still go in and test models for example, exciton binding energies. This is what we've done here. Excitons are a bit tricky in 2D. They're much more difficult to describe in 2D than 3D due to non-local screening. So we have a model for exciton binding energies that depends on just the polarizability. And here we've tested this model against the actual calculated BSE exciton binding energy, and we see we get some good correlation. So one can use it to test models, even if some of the materials are not very realistic. So we would like to calculate the topological properties of all these materials in the database, see if we have topological insulators. And it's known how to do this for a particular material. However, it can be a little bit tricky to do it in an automated way. One way to do it is to use 1U90 and Z2PAC. For example, if you have an interface to your DFT code to these codes. But it can make it a little bit tricky if you want to do this for a lot of materials, because these intermediate steps can sometimes cause a little bit trouble. So instead, we have calculated k-space Barry phases for directly from the block states. And so the idea is we have a 2D Brillouin zone. And for each, say, K2, we define a 1D Hamiltonian. And for that, we can calculate the Barry phase along here. And we do that for each K2. And if we do this for all K2, then the Barry phase should return to itself from one end of the Brillouin zone to the other, except for a multiple of 2 pi. And this multiplum here is the Chern number. Okay, and we can also do this. This is just simple example. If you have one band, but if you have multiple bands, we set up a Barry phase matrix that is diagonalized, and we use this parallel transport algorithm of Massaro and Vanderbilt to do this. So just here's how it would look like. The Barry phase can move like this. Then that would indicate that we have a Chern number of 1 with just one band. But if we have time reversal symmetry, we may have the possibility of have this a quantum spin Hall insulator, and then the Barry phases would look like this. The point here is that at the time reversal invariant points, the Barry phases are forced to be degenerate, and one can just look at any point, any horizontal line, half the Brillouin zone, and count the number of crosses, and that will give us the C2 index modulo 2. Okay, so this has all been outlined before. So the nice thing here is just that it's done just from the block states directly, so we don't have to do any intermediate steps. So here's just a few examples. One material, iron bromide, which is predicted to be stable. It has a very small Cohen-Charm gap. Perhaps you can see the gray lines here, band structure without spin-orbit coupling. So it has a Dirac point. With spin-orbit coupling, it opens up with this band gap. It's below the convex hull, so we actually believe that this should be very stable. And now if we do these Barry phase calculations just for the 4 valence bands, which are isolated here, we get this structure here indicating that it has a Chern number of 1. So this is one example of another example is stannine, which is like graphene or silicene. It's just tin instead of carbon or silicon. The advantage is that it has somewhat larger band gap, and there is some work going on about stabilizing this on surfaces. And in addition to time reversal symmetry, this also has inversion symmetry, meaning that all bands here are doubly degenerate. So it means there's actually 4 bands here. And if we take these and do these Berry phase calculations, we get this plot here, and we can see that if we look at half the Boulogne zone, there's 1 or 3 crossings everywhere, indicating that it has a Z2 index of 1. The final case example I will show is this tin telluride. This is also a known 2D materials. It's been predicted to be a mirror crystalline topological insulator. Has a gap of 28 milliV. So rather stable. I don't think it has been synthesized yet, but it could be possible. In this case, we can see that it's not a quantum spin Hall insulator. There's 2 crossings everywhere. So it has Z2 index of 0. But on the other hand, we can see that because it has mirror symmetry, we can identify, for example, this one with a mirror turn number of 2. And then there's the other ones going the other way here, which is the other mirror states. This is an example of a material that has a mirror turn number, but it's not a quantum anomalous Hall insulator or a quantum spin Hall insulator. But still, I mean, the mirror symmetry is in the plane, so it still means that any edge you consider that conserves this in-plane mirror symmetry will have protected edge states. So we've done this for all the insulators in the database, and we of course find a lot of the known topological insulators. So most of these have been predicted theoretically. Some of them has been studied experimentally. There's also a few known ones which are not present here. For example, tungsten ditelluride. And the reason is simply that PBE predicts that this is a metal. So we've stuck strictly to PBE here, and if PBE doesn't give the right band structure, then it's just too bad. It won't show up in our calculations. Then we found some new quantum spin Hall insulators. All the ones that are marked in bold here, the ones that are dynamically stable. We've also done it for those that are not dynamically stable, but these are probably irrelevant in this context. We see that most of them has rather small band gaps, but I want to note these 3 here, which is antimony halides. They have quite significant band gaps on the order of half an eV, and we also predict them to be very stable. They're below the convex hull and have rather small heats of formation. But there's so far not been any attempts to synthesize these yet. And I should really say I'm not in a position to say if this is possible or not, but we can just see that the experimental techniques for bottom-up synthesis of 2D materials is developing very rapidly. So perhaps someone will come up with a method to synthesize materials like this or other ones one day. This is just an attempt to be a bit suggestive about what materials could be interesting to look at if you're very good at synthesis. So we also found new mirror crystalline topological insulators. We have mirror turn numbers ranging from 1 to 3. And it's worth noting that if we have mirror symmetry and time reversal symmetry, then we are guaranteed that the Z2 index is given by the mirror turn number modulo 2. Because I mean, you can maybe convince yourself that because all the Berry phases have to have reflection symmetry around the gamma point. So if you look at these spectra, you can see that it has to be like that. And then finally, we found 6 new quantum anomalous Hall insulators, which I think is they all have very small gaps, except so this is a milli-eV, except this MOS2, which is it has an energy of 1 eV above the convex hull, so it's likely that this will never be synthesized. But the other ones, maybe not. At least again, I mean, if you want to study turn insulators, for example, magnetoelectric properties or let's say optical properties of turn insulators, then you have a set of real materials you can start dealing with here, and then we can worry later if it's possible to actually make these. There's a few materials which are also interesting that didn't make any of these lists. For example, osmium O2. I mean, all these churn insulators are, they have to be magnetic. There has to be broken time reversal symmetry. Otherwise, we cannot have a finite churn number. And it's all driven by spin-orbit coupling. So it means that there's always a preferred direction for the spins. There's an easy axis. On this case here, there's an easy plane. There's lastly magnetic isotropy in plane. And this material is a trivial insulator, and it has an easy plane. But now if we rotate the spins out of plane, you can see that it makes a transition. So this is in plane. If we rotate out of plane, at a certain point where the gap closes, and after that it becomes a quantum anomalous Hall insulator. It means that you can actually induce such a phase transition by applying a magnetic field in a particular direction. And the magnetic anisotropy is very small, so you can do that. You can do this without actually destroying the electronic structure in this material. So this way, it should be possible for some of these materials to switch between different topological states. But I would like to say that, I mean, a lot of people have studied and tried to predict new churn insulators, new 2D materials showing this behavior. But a very important point in 2D is that magnetism is very, very hard to come across in 2D due to the Wagner theorem. And so one really has to worry about whether or not these materials are actually magnetic, even if DFT predicted to have a magnetic ground state. Because the Wagner theorem says that you cannot have a spontaneous broken symmetry at finite temperatures. If t equals to 0, which is what we do in DFT, it's fine, but not at any finite temperature. So 1 millikelvin, it's gone. You cannot have break the symmetry spontaneously. You can break it explicitly, though, and this can give rise to magnetism in 2D. This was discovered 3 years ago in chromium iodide. The thing about chromium iodide, it has very strong out-of-plane magnetic anisotropy, so that breaks the symmetry explicitly and allows for magnetically ordered states below 45 Kelvin. So I think whenever one is dealing with a magnetic material in 2D, we really have to worry about this and see, okay, is the magnetic anisotropy present? Can this order at finite temperatures, even though DFT tells us that it's magnetic? So it's too complicated to do the thermodynamics directly from DFT. That's not really possible. So we need to go to some model in order to do that. And a very famous model for this is the Heisenberg model. At least for insulators, this has been shown to provide a very good description of magnetism. So we just have a spin operator for each atom that carries the magnetic moments, and then there's exchange couplings J that couple the spins of different atoms. A somewhat simpler model is the Ising model, which only considers the Z component of the spins. This is much easier to handle because it basically becomes a classical model with discrete states at these discrete values of a Z. Now, if we look at chromium iodide, this is often referred to as an Ising ferromagnet because it has a very almost rectangular hysteresis loop. It means that you go up here, the spins flip instantaneously. I mean, they point either up or down. So this is called an Ising ferromagnet. And I think the terminology is a good one, but just doesn't mean that the Ising model is a good model to describe the thermodynamic properties, which I will show a bit later. So this has been done a few times, but I would really encourage not to use the Ising model to model any real magnet. It's good for a lot of things, but it's not very good for magnetism. And then finally, the mean field theory. This is the simplest thing you can do in 3 dimensions. It often gives a rough estimate of the Curie temperature. And if we have the Heisenberg model, there's only one energy scale, and that's the exchange couplings. And this essentially says that the Curie temperature should be of the order of the exchange couplings, right? Then there's some factors in front. But that doesn't work in 2D. We know if the system is isotropic, like this model here, then the Curie temperature is 0, always, regardless of the strength of the magnetic interactions in the system. So it's not enough just to have the exchange couplings. We also need to have include anisotropy. And there's 2 Well, there's two terms you can include in the Heisenberg model that includes anisotropy, the single ion anisotropy, and then anisotropic exchange. This one is essentially saying that, well, the coupling between the C components is different than the ones in X and Y components. So here I've assumed that we're dealing with a system which is isotropic in plane, but have an out-of-plane anisotropy. And now these parameters here can be obtained from DFT by considering different spin configurations. If we just consider nearest neighbor interactions, so we have one exchange coupling, one single ion anisotropy, and one anisotropic exchange coupling, and that's three parameters we need to extract from DFT, and we can do that from different spin configurations shown here. And in principle, if the Heisenberg model is a good description of the system, then this should be exact, because at least if we have a good functional, DFT should give the correct energy for a given spin symmetry in the system. So that should be a viable route to map DFT calculations into Heisenberg models. Now then, in principle, we know what to do. We can calculate magnetization at any temperature by this expression here, with the partition function given here. And then we just figure out at which temperature does the magnetization vanish. However, it requires that we know all eigenenergies. And even in the Heisenberg model, although it looks simple, it's an interacting model, and we cannot just solve it to calculate all the eigenenergies of the system. So we cannot just do this. We need some approximations. And we consider two approximations here: renormalized spin wave theory and classical Monte Carlo simulations. I think these are the most common approaches to this. So first, the Monte Carlo simulations. This is assuming that the Heisenberg model is a classical one. Just set up a very large unit cell of your magnetic lattice and do these calculations. And we've done this for three different values of the anisotropy here. See, as the anisotropy goes to zero, the critical temperature, the point where the magnetization here vanishes, also goes to zero. If the anisotropy goes up, the critical temperature also goes up. So this is as expected. The dots here, by the way, are the magnetization. It's a function of temperature, and the solid lines are the heat capacity, which has a divergence at the Curie temperature. So that's probably the easiest thing to track down if you want to calculate the critical temperature. You might worry about this classical treatment of spin 1, spin half, or spin 1, spin 3 half system. It's not obvious that works. So a somewhat orthogonal approach is this spin wave theory, where we really take the quantum operators and then write them in terms of some creation and annihilation operators that create fundamental magnetic excitations in the system. And one can show that if we take these operators to satisfy bosonic commutation relations, then the spin operators will also satisfy their commutation relations. So that's good. But of course, we have this square root, so we have to expand that, and it means the Hamiltonian becomes a power expansion in these A dagger and A's. We just take the H0 part here. That's the part which is quadratic in raising and lowering operators. That can be diagonalized directly. This gives this energy dispersion. Depends on the J's here. This JFQ is given by this expression. And importantly, we see that it has a gap. I mean, it has a minimum if Q is equal to 0, that this is 0, and then this is the fundamental spin wave gap in the system. And this is what required to break the Merrin-Wagner theorem, that we actually have a gap in the spin wave spectrum. Right, and we see it depends on these two anisotropy constants. We can also take interactions into account. The spin wave theory is very good at low temperatures, where we typically have one magnonic excitation at a time. But if we're getting close to the critical temperature, there's a lot of excitations in the system, and there's no reason to expect why this should work. And we need to take its interactions into account at some level. And what you can do is you can take fourth order corrections into account and then do a mean field approximation on that. And it's sometimes referred to as renormalized spin wave theory, or RPA. It's more like a Hartree-Fock, actually, thermal Hartree-Fock, I would say. So now if we do that, we compare. The black line is the classical Monte Carlo simulations, if we calculate the critical temperature, well, the critical temperature in units of J or A squared, the classical, that only goes in as, so we can do that for all values of spin. For RPA, it depends a little bit on the spin system, if it's spin half, spin 1, spin 3 halves, and so on. But it gives very similar results. But one important point to note here is that the RPA result just becomes linear at some point. Now, what I've shown here in the dotted line is the Ising limit. That's the result for the Ising model. And if the anisotropy goes to infinity, then the model effectively becomes equivalent to the Ising model. So we know that these lines has to go asymptotically to the Ising limit, and the RPA does not do that. So we think that the RPA doesn't capture the correlation properly. So the RPA is a quantum method, but it's very approximate for the correlation part of the problem, whereas the classical Monte Carlo simulation has all correlations, but it just neglects quantum effects. But the point is that near the critical temperature, quantum effects tend to be quenched by thermal effects, so it's not a very severe approximation to do a classical approach at that point. So we will stick to the classical Monte Carlo simulations. Now we can do this also for this, what I showed was for a square lattice. We can do it for honeycomb lattice and hexagonal lattices also, which is the most common ones in these 2D materials. It looks very similar. Again, these have their own Ising limits. And now these lines are very suggestive of a fit, so we don't have to do the Monte Carlo simulations every time. By the way, I mean, I've shown this for very large values of the anisotropy in order to show that we actually reproduce the Ising limits correctly, but chromium iodide, which has large anisotropy, is all the way down here, with A over J equal to 3. But it also shows that the Ising model is not a good one. I mean, you overestimate the critical temperature by a factor of 3 if you try to use the Ising model to do the thermodynamics of chromium iodide, even though it looks like it's Ising-like from the hysteresis loop. But we don't want to do these Monte Carlo simulations for all materials. I mean, even if it's classical, it's still very tedious work. So instead, we fitted all these. We can fit all these results to a universal expression of this form here. We just have the nearest neighbors, and that's 3 for honeycomb, 4 for square, and 6 for hexagonal. Then it fits all of them, and then we have some fitted parameters, this one, and this one, and then we have the Ising critical temperature, which is the asymptotic limit of the expression. And these have been tabulated for all lattices in 2D. So these can easily be looked up. So it depends on the spin wave gap, which is here, and the exchange coupling. That's all. When we have that, we can estimate the critical temperature. So this is a simple descriptor, but still it gives a rough estimate of the critical temperature. For chromium iodide, we've done this with PB plus U. We get these values, and we get a critical temperature of 50 Kelvin. So experimentally, it's 45. But again, much better than the Ising model, which is 3 times larger. So I just want to mention that these results are of course only as good as the DFT we use to extract the parameters, and it turns out it's rather sensitive to the functional we use. We get different results if we use PV-SOL or LGA, and here I just show the dependence on U. The critical temperature can go from 30 Kelvin to more than 50 in these range of U's. The spin wave gap doesn't change so much, so that's a spin orbit effect, so it's not that sensitive to the choice of functional. But the other parameters are actually rather sensitive. So I think this maybe should be regarded as the uncertainty in these kind of calculations. So if we go back to the C2DB, it has 786 ferromagnetic 2D materials, and it's only 150 of these are stable. And 12 of these are insulators with a positive spin wave gap. We're not very fond of dealing with metals because, first of all, the Heisenberg model is probably not very good for metals. And second, the energy mapping analysis used to extract the parameters is is ill-defined for metals because the spin will change when you change spin configuration and so on. So we will stick with insulators for this problem. Here's just a scatter plot of the exchange coupling and spin wave gap of all the materials. Again, it may be a bit weird to have negative spin wave gaps, but whenever you have a negative spin wave gap, that's because we start out with this Holstein-Primakov transformation, assuming that the spins are out of plane, and if the easy axis is actually in plane, we get a negative spin wave gap, signifying an instability in the problem. But that's fine, because we don't want materials with negative spin wave gap, which have in-plane anisotropy and easy plane. Because if you have isotropy in plane, there's still a continuous symmetry in the there's still a continuous spin symmetry, and the material cannot be magnetic by the Mermin-Wagner theorem. So this is more table. Again, one should look at the ones which have a green background. These are the insulators, and we get spin wave gaps on the order of approximately 1 millieV. So these are the materials we find. A little bit disappointing, I think, because the best ones are the ones that are already known. Actually, these chromamidite, bromide, and chloride seems to be the best ones. We find one that we predict to have a larger critical temperature, manganese oxide, but that's basically all. And then we find a few other ones with very small critical temperatures. I should say these are calculations done with PB plus U. If instead we do it with PB, we get a different set of materials, and the ones that are in both phase here are the ones where we get magnetic order for both PB and PB plus U. So let me move on. We've also tried to do this for the ICSD and COD. I think this is a more relevant approach if we really want to predict new materials, because all of these are bulk materials that have been predicted or measured experimentally. So one has to figure out which of these can be exfoliated into 2D materials. So we start from 150,000 bulk materials from these databases, and then we identify 4,000 that can be potentially exfoliated. And we use some geometric 2D scoring parameter. There's other ways of doing that. The group of Masari also did a similar study based on exfoliation energies of all these materials. And then we do DFT calculations for these, and there's 55 of these which has a ferromagnetic ground state. And again, there's a scatter plot of spin wave gap and exchange coupling. We find for we only want the ones that has a positive spin wave gap, and we actually also only want the insulators because we don't know how to treat the metals yet. So we do find some, here's a list, most of them we don't. It's again reassuring that we rediscover the known ones, chromamidite, for example, chromium bromide, and chromium chloride, which are known to be magnetic 2D materials, and then we discover a few other ones, which could perhaps be interesting to look into. But it's not a lot. It seems to be hard to come by. Given that we start with 150,000 materials, this is the complete list of the ones that has critical temperatures above 10 Kelvin. So finally, I would like to acknowledge Daniele Torelli, who did a lot of the work on the magnetism. He just handed in his PhD thesis on it, and Christian Thyssen, who initialized and conducted most of the construction of the computational 2D database. And finally, there's a lot to do in this field, I think. Antiferromagnetism in 2D is not that well studied. There's a few experimental and theoretic reports, but again, one needs to figure out how to calculate critical temperatures. Then there's quantum corrections to the energy map analysis. We assume when we do this that an antiferromagnetic state can be mapped directly to a DFT calculation, but it turns out this state is not even an eigenstate of the Heisenberg model. So it doesn't really work, it's not expected to work that well. But one can include these corrections and find the proper ground state for antiferromagnetic configurations. And finally, the most important problem is metals. It's not really known how to do all this for itinerant magnetism. So one can do TD-DFT, and we're trying to do that where you can get actually Magnon dispersions, but this is what would correspond to linear spin wave theory, and it's not something that we can calculate Curie temperatures from, but we'll see. Okay, thank you for your attention.
Thank you so much, and we're open for questions. There used to be people with microphones.
So to predict the topological insulator, you are using the PBE.
Yes.
But I mean, it may be that PBE is just predicting topological insulator that are not. So can you comment on that?
Yes and no, but you're right. I mean, it could be that PBE are wrong. Is wrong. I mean, it's. I think there are examples where you see that different functionals give different predictions of the topology. But I think mostly that different functionals will predict the same topology. But I'm not so sure about it. But we tried, for example, this material I showed you, iron bromide, which is we predict to be a Chern insulator. If we add a U to the iron D states, a U of 1 eV, then it's a trivial insulator. So it's. Yeah, it's. I don't know how much I will try. I will trust this. I mean.
I think I have a counterexample of TINI that is a topological insulator in DFT and trivial in GW.
Right. Yeah. Yeah.
Yeah.
Yeah.
Hmm.
Miguel.
I have two questions. One is related to the prototype search.
Yeah.
There is always the danger, the very present danger, depending actually on the prototype, that it's not the ground state, and actually you get something that is quite above the ground state.
Yes.
So did you try some structural prediction? This is the first question. That will that give you an idea of if the thing is really close to the ground state, to the two-dimensional ground state for the composition?
I mean, do you mean the structure is not the most stable one? I mean, you can have other structures.
Even in 2D. Even in 2D, this could happen. I mean, this is very typical in 3D, right? You do a prototype search, you think it's a perovskite, and then the thing completely deforms and gets into.
Yeah, I mean, for example, for MOS2, we have MOS2 in maybe 5 or 6 different prototypes, and then we've listed them according to stability. I mean, and then we know that the 2H phase, which is common, we can see that's the most stable. And then there's all the other ones, which are less stable. But then there's the 1T phase, for example, which has been identified and isolated experimentally. It's less stable, but still people can work with it. So that, I mean, we're certain that we find materials which are not the ground state. But we also have examples, experimental examples, where people have isolated these materials and worked with them, even though they're not the ground state. For example, MOS2 in the 1T phase.
So I go to my second, if I may. If I saw properly, most of the materials that you had with negative distances to the convex hull were bromides, chlorides, and were halides. My question is, how is this just an artifact of the PBE, or is it that we simply don't know the three-dimensional bulk?
I mean, we do this with respect to the convex hull, including both 2D materials and 3D materials, but I mean, we don't know, of course, if we have all the right materials, all the proper ground state.
But you agree with me that if you just put layers out of layers, you should get something even lower in energy.
Yes. That's
so there should be a three-dimensional material that is unknown. And that's a bit strange, because you have relatively simple and straightforward compositions. So what's the problem here?
Oh, it's a good question. I mean, but these materials may be very hard to synthesize in this. Also from nature's side of view. I mean, it may be very difficult to make these structures. Maybe it needs some precursors that are really unstable. So that could be one explanation. But I think it's more probable that it's a problem with the calculations, that something is not taken proper into account, maybe with PBE, as you say.
Two last questions, quickly.
So you have a very impressive list of materials, and I was just looking at your iron selenium, where you get it unstable. You get it unstable, why? Because you're looking at ferromagnetism in the system, which we know is not ferromagnet. Where do you get the instability in the system? I mean, we know a lot about iron selenium, so it's a high TC superconductor, and if you strain it a little bit, it will go into a stripe magnetism, so antiferromagnet, not ferromagnet. You will never get it ferromagnet. So when you say here it's not stable, in which sense it's not stable? You had, exactly, that was your table.
So you say iron selenide?
Yes, for instance, and you had iron sulfur also.
Yeah, I mean, I mean, the magnetism is stable in the high TC superconductors, so it's stabilized by the interlayer couplings typically. So
well,
if you have
the
it,
system is pneumatic, so
but still, if you have it in a pure, I mean, that's what people always assume. Magnetism is because, I mean, people neglect interlayer interactions, but that's really what stabilizes magnetism in that case. I mean, here we have the pure 2D form, and that's so I think that's not in conflict with the.
No, but the question is because you're looking here for ferromagnets. So why would you expect that this system would go into a ferromagnet? That's my question.
Well, again, this is PB calculations, and that's what we did, and most likely PB is not very good for this kind of material.
Ferromagnets, maybe there you have more chances.
Yeah, but I mean, you could do all this for PB plus U, right, or another functional, or different U values, and you're likely to get different results. I mean, I think so, yeah. Yeah, that's true. I mean, yeah.
Well, just one question. It's impressive, the list, but we just will focus on the oxides. You have manganese oxides too. I think there are some experiments concerning the magnetic measurements of this compound. So, and they have something like contradictory measurements, whether it's antiferromagnet or ferromagnet. And the other, that's just a comment. And the other question, and the question is that the U value you have to use for these oxides, because it's very different from the metals side only. So they should be much larger than the, if you use a U for these oxides, should be much larger than the one that is not commonly used for the metals. So that.
Yeah, I mean.
And if it can change from ferromagnet to antiferromagnet, or I don't know, they localize so much the magnetic moment on the ions that.
It's true. I mean, so again, what we did here is just screening based on PB, right? And we are aware that PB might be wrong in a lot of cases. You do PB plus U, and you have to figure out which values of U to use, and so on. It's not trivial, I think, to find the right functional for this. But
great, Thomas. I think I have to stop the discussion so that we stay on time. So thanks again to the speaker.